Okay, let's get started. So before we go go back to wind energy, any anything you want to change going from the midterm to the final, right? So the final will look very much like the midterm for this class. So it'll be essentially the same format, same length, same style of questions. So any issue with the midterm that you like to see change for the final? Anything you think we can do better on how the exam is set?
I think it's okay.
Okay, so we're all okay with the midterm, then yeah, so we're all okay, then the final will look almost exactly the same as the midterm. Right, and also this class is not very cumulative. So basically so the final will also cover a bunch of areas, and then that's be similar to the midterm.
Is the final is gonna cover only like half from here, right?
Yeah, so final will cover after solar, right? So from wind until whatever we get to by the end of the class. Yeah, because we have covered a lot of topics in the class, but none of, a lot of them are not very related to each other. So final will be, think of final as a second midterm, I guess. That's for maybe a better way to call it. Okay, so then we'll, final will be similar in style. And then so also over a day, and we'll have 2 hours of office hours in that time. All right, so let's remind ourselves where we are in the class. So last time we covered wind energy, right? We started covering how wind turbines work. And as a reminder, we have a blade. Right? We have a wind turbine blade. Then really the wind turbine works because Newton's third law, right? So this is the blade of a turbine. And if you have air blowing this way, then it works because you're bending air downwards, right? And we can generate lift because we're bending air downwards. Right? So Newton's third law says if the air bends down, there is a force upward on the airfoil. Right? So the airfoil experiences force going upwards because Newton's third law, and that's how we generate lift. So there's multiple components of lift. Right? So if you can look at the force that's being exerted on this airfoil as, again, this is our airfoil. Let's say we have some angle of attack here. And then we have a lift force, right? This is the force that moving you up. We have so normally if this is airplane, then you have a thrust, then you have drag. And so for airplane, you're actually moving in space. You're moving back and forth. You're moving forward in space. But for a wind turbine, we really don't care about the thrust or the drag, right? Because the wind turbine, the blades are fixed on the tower. So for wind turbines, really what you want to do is we want to maximize the lift. Right? So wind turbine is the wind turbines or wind blades, we want to control lift. Okay, we want to change how much lift the blade is, how much lift the blade we have on the blade, and then that will change the power generation. That will change the speed that the turbine turns, and then we'll change the amount of power we can generate. Okay, so if you're more interested in sort of airfoils and how airplanes work, so you want to see some more fancy simulations, then you can look at there's sort of NASA websites that's devoted to showing this kind of pictures. But for us, what we care about is mainly generating torque, right? The way we get power is if you look at the front view of a wind turbine, we generate lift, but then since this thing is, on the blades are fixed on the tower, then the lift gives you torque, right? So torque, this mechanical torque turns into electric power. That's the way we generate power from the wind turbine. So we have mechanical, so lift gives mechanical torque. This becomes electric power. Right, so the torque is used to turn a generator gives us power. So lift is of course related to how much torque you can generate, right? So lift is related to torque. So we look at the torque and lift equations. Okay, let's think of mechanical torque and the lift equations. So if I have a wind turbine, let's say a 3-bladed wind turbine, and I'm generating some lift. I have some lift force on the turbines. So all of this is generating some lift force. But how do I relate that to the torque? So if I'm given the force of the lift, what is the torque I have? How can I compute the torque? I remember. Length of blade, right? So the chat suggests equals to X, this is the length, F lift. So we need to be a little bit more careful, right? Is this length the length of the blade or something else?
The length from the center to where like the force is being exerted.
Right, so we have to, right, so this is the length to the center of gravity, right, or center of mass. Right, so this X is not really the length to the tip of the blade, but then the length to the center of gravity. So you look at all these blades, we have some center of gravity or center of mass. Then X is this distance, right? So you can treat the blade as a point mass at its center. And then if you take a look at that distance multiplied by the force generated, we'll have, that's the amount of torque we have. Okay? So this tells us basically the amount of torque is directly proportional to the lift, okay? To the lift force. So when we control the blade or when we control the torque, it's basically the same as controlling how much lift force we have on the blades themselves. Okay? And one thing we should always remember is for wind turbines, it's not more lift the better. Right? So we often want to we want to control the amount of lift we have on the blade. Sometimes we want the maximum lift or the maximum torque. Sometimes we don't. Okay, we don't necessarily always want the maximum lift. Right? So the operation of blade is actually, we have wind coming in, right? How do I get the power I want? That translates to how do I get the correct amount of lift on the blades I want? That's our control question. So this is similar to solar, where in the solar, the power is determined by the voltage as the output. Here, the power is determined by the amount of lift. So let's look at how we control lift. So we control lift essentially by controlling this thing called angle of attack. So angle attack as a fancy way of saying this is your blade. What angle do you make to the incoming wind direction? So if you look at the slides, then we always reference angle attack to the direction that the wind is coming in. Okay, so this is the wind direction. And then the angle of attack is the angle that your blade makes with the direction of the wind. Right? So this you can be 0 degrees, meaning your blade is that's the top picture. You're facing directly to wind, or it can have some positive angle. That means you're opening up to wind. Right? And different angle of attack control. So the lift is really a function, or the torque is really a function of the angle of attack we have on the blades. So if you look at angle of attack, so when you first increase the angle of attack, you basically get more lift because again, you have wind coming in this direction, you have wind going downwards, so increasing angle of attack from 0 degrees increases lift. Right? So this is saying we can change lift just by changing the angle. And then if you look at this more closely, basically we can think of the force into two components. Right? If you look at the force generated on this airfoil, on this blade, we have a force that's perpendicular. Right? So first we have a force that's perpendicular to this blade. Then only part of the force is useful for us. That's a lift. Right? Only the lift force is useful for us. The other part is the drag, and drag is not very useful for a wind turbine. Okay? Since we're turning this axis, having a drag is not that force doesn't generate power. So if you look at the angle of attack, and when we increase the angle of attack, what happens is basically when you start at the horizontal position, right? So wind is always coming in from this direction. When you have a horizontal direction, all the force you get is a lift force. You're gonna think most of the force you get is this lift force, but it may not be very large. So when you have a larger angle of attack, you have a much larger force. Some of it is lift, some of it is drag. And so when you increase the angle of attack, you increase the total force you generate on this blade. You increase the total force you generate, so you may get more lift. But then eventually you can increase your angle of attack too much. Right? At some point, it becomes very steep. Right? The angle of attack becomes very large. Then most of the force you generate is actually drag and not lift. Okay, so you want to find a sweet spot, right, to generate the right amount of lift force, okay, for the angle of attack by changing your angle of attack. Right? And what happens when your angle of attack is too large? So can we operate at angle of attack very large, let's say close to 90 degrees?
The lift force is getting smaller and the drag getting bigger.
So that's fine, but then what happens there?
You might just break your propeller. I don't know, or the turbine. I mean,
So why would you break your propeller or turbine? Like what breaks it?
there's too much drag force. I don't know.
Right, so that's not really. So there are cases where we don't want the turbine to turn, or we don't want to turn very fast, even though there's drag force. Right, what really happens is if your angle of attack is too large, sometimes you can have something that sort of creates a lot of turbulence. You have a lot of turbulence being created at this wake. And then you have turbulence. And then what you have, basically, this is like an airplane that stops. You have an airfoil that stops. And this can reduce the lifetime of your airfoil, right? This is not good for a blade. Right? So you have a blade that's, is in the stalling regime. So there's a lot of turbulence. The blade maybe, there's a lot of oscillations or shaking of the blade, but that cause a lot of mechanical stress. Right? So often we want the angle of attack not to be too large. Okay, so now theoretically you can operate an angle of attack anywhere from 0 to 360 degrees, right? But what you really want to do is you want to operate at a reasonably small angle of attack. So if you look at the function of lift as angle of attack, so alpha is our angle of attack. This is how much lift we generate. At 0 angle, we still generate some lift. So if you look at it, basically go something like this. There's some negative angle where you have 0 lift. And then here you have the stalling region. This is where you stall. So when you operate, what you want is this is your operating region. You want to keep your blade away from a very large angle of attack. Okay? You want to have an angle of attack that's sometimes higher than 0, but not too large. And when you don't want any lift, right? For example, you may not want to generate any power. Then what you do is you have a negative angle of lift, right? You pitch it negatively. That way you can also have no lift, but you do not go into the region where you're stalling too much. Any questions about these?
You said that sometimes you don't want too much lift. Why
Right.
is that?
Oh, so let's say your wind turbine is disconnected from the grid. Right, let's say a fault happens on the line connecting the wind turbine to the grid, and the fault happens. Then if you have lift, that's torque. Torque has to go to the right. This torque has to go somewhere. So it's connect to the grid. This is electric power going to the grid. But if you disconnect from the grid and you have all this much power, it has to go somewhere, and your turbine may fail. So it can happen that your turbine will fail if you have too much power and the power doesn't have somewhere to go. Any other questions about this? So let's see if I can find an example to show you guys. So can you guys see my screen? The other screen?
Yeah, we can see it.
All right, so this is what happens when you have too much lift. Okay, so wait for it. All right, so you have a very windy day. You can't get rid of all this electric power. But then, so you keep spinning faster and faster, faster and faster. Eventually, your power has nowhere to go, and this is what happens. Okay. All right, so you can find a lot of examples like this on the internet, right? So you can, if you want to go to YouTube and just Google wind turbine failures, that's what happens. Okay. So for wind turbines, a lot of design is not, I guess a lot of design is about how to generate power, but an equal amount of design is how do I get rid of this power? How do I get rid of unnecessary power? So it's, nowadays it doesn't happen as common as when you have a wind turbine that just blows up and flies apart, but does still happen, right? So this is where you want to change your angle of attack. Right? You don't want to have a lot of wind. Either maybe too much lift, more lift than you can handle. Any questions about that? Yeah, so I suggest if you have some free time, go on YouTube and watch some of these videos. There's sort of really tells you what goes wrong if you don't get rid of the power, right? So You're interested, you can take 451, which is wind energy. I'll teach that course next winter. A lot of that course is, right, if I have wind turbine that's spinning and I have a fault, I can't get rid, still have mechanical power from wind coming in, but I can't get rid of this electric power, then what do we do? How do we protect it? Oh yeah, so next we'll cover how they change their angle of attack. So every wind blade has the ability to change their angle of attack. All wind blades have this ability. So this is, like an airplane wing that can, every blade has this capability. And what we have on this blade is called the pitching of the blade. And the reason it's called pitching of the blade is the following. So remember when we talk about angle of attack, right? This is the wind direction. This is the wind direction. But in practice, we often don't know what the exact angle wind is coming in. Right? So it's a three-dimensional space. Wind is coming at some angle, and the angle of attack is measured with respect to the direction of wind. That we may not always, most times we don't know what this is. So it's hard to talk about angle of attack. We don't know the wind direction. So what we do in practice is to talk about the angle that's complement to the angle of attack, which is this beta angle. So beta is called the pitch angle. And the pitch angle is just measured from the center line. Right? So the pitch angle is measured from the vertical line that goes through the blade. And we want to talk about the pitch angle rather than the angle of attack, is because we don't know the wind direction. We don't know the wind direction, so we can't talk about alpha that easily. But what we do know is we know the pitch direction. So we have often, or most of the time, think of controlling the blade as controlling the pitch angle, whereas the angle is just the angle the vertical axis makes. And the center core line going through the turbine and the vertical axis makes the angle called beta. And by changing beta, we're indirectly changing alpha, right? So this is really control alpha by changing beta. So fundamentally physically, we want to change the angle alpha. We can't because we don't know the wind direction. So we use something easier to measure called beta, and then we change beta. Okay, we change the value of beta. So if you look at the wind turbines, basically the way they can do the pitch is all these blades can turn. Right? They can all turn on this axis, and this will change the pitch angle. This is all blades. Now all turbines can do this. Right? The three of them will turn, and this changes the pitch. And by changing the pitch, that will control how much power we generate out of this. Any questions about the pitch angle?
That's really interesting, but I have no question yet.
Right. So if you look at wind turbine, a lot of the engineering is not exactly making the blades as the control, the feedback control mechanism around the blades. How you adjust pitch, right? How do you measure the power? How do you relay that to the pitch and all that?
Is it possible to change the pitch, like rotate these blades automatically based on the sensed wind direction?
Oh, they're all automatic. All these are automatic.
Okay.
There's no human in the loop anywhere for this. This is, so if any of you taking embedded system or using microcontrollers, you have microcontrollers controlling all these. There are some sensor. So wind direction normally is hard to measure. We don't really measure the wind direction. It's also not all that well defined. What we do is we measure the output power. So we have a power set point we want to generate. let's say this turbine wants to generate 1 megawatt of power. I sort of know I should, increase pitch to generate more power. I sort of know that relationship. So I can measure as if my power generation is larger than my set power, then I should reduce my pitch. If my current power generation is smaller than my set power point, I should increase the pitch. So you have this sort of feedback control loop that's just running in all this place. Right? So again, if you are taking control system class or are you going to take it, this is actually a very good example of a feedback control system. You measure power, you change your pitch. Of course, it's not linear, there's delays and all that. But at a high level, you can think all these are automatically done. All these are automatic. So there's lots of logic building into all this pitch. So the idea is, right? So what I do is, again, the feedback loop is, let me measure the power I'm sending out. Right? So that has to do with the torque, that has to do with the lift. So I change my pitch angle to change the lift to control the amount of power I generate. Again, to avoid the video I showed, right? From a wind blade perspective, wind turbine's perspective, as you do not want this thing to blow up. Okay, you don't want this thing to fall apart. Right? So there's a lot of control mechanisms, a lot of fail safes, a lot of things that goes on wind turbine. Right? So then, if you want to take a even closer look inside of the turbine, is on the blade you can do pitch. Inside the housing of the turbine, you have a generator, you have a lot of gearboxes, you have a lot of mechanical systems that's controlling this turbine. So it's quite an intricate engineering problem. It's quite intricate how you deal with wind turbines. And by depending how you engineer this, it makes a big difference how efficient your turbine is. So again, nowadays, a good turbine and a bad turbine is really not for the material or things like that. As one, can you build it cheaply? Two, as do you have advanced controls on it? Right? How good are your control loops around the turbine? Okay, so any questions about the sort of physical setup before we do more math on this?
So like you're saying, like we rotate the blades to avoid those breakdowns where like the wind's spinning so fast that it's like producing too much power, right?
We do it for two reasons. Right? One is to not produce too much power. The second is, right, we may want to track the sort of a power production point, right? So wind changes. So if you don't change the pitch and the wind direction or the wind speed changes, then your power output will change. But often we want that power output to be a constant value. So we'll change the pitch trying to track that power output.
So like if it's producing extra power, like why do we want to keep it constant? Like isn't extra power good? Or like couldn't we just overbuild stuff so if it does produce extra power that like that's okay and we can capture that?
No. So in a power system, extra power is not good. Right? So what we want is the load equals to the power. Because conservation of energy, extra power has to go somewhere. Right? We don't have a cheap way of storing extra power yet. So if I'm an operator perspective, if I know what my load is, I want my generator to produce the amount of energy that's required by my load, not extra ones. Right? If it's extra, I don't know what to do with it. Okay? So for example, if you have wind, what you observe is, let's say you're in the Midwest, and then let's say your summer night at Midwest, what you see is the price of electricity is often negative. The negative price means, please consume electricity, I'll pay you. Right? So that means we can't get rid of power that easily. We have to pay. Right? If it generates too much power, I have to pay people to take that power. And even worse is really when you have a fault. Right? If you have a fault, so wind farms are large. You have transmission lines running around this wind farm. And let's say you have a lightning strike on the line. So the line goes out of service. there really is, how do you dump this power that goes into the turbines, right? That's time when you really have to dump the power, right? If you can transmit this power to the grid has extra power. The grid doesn't know what to do with this power. The grid is not happy to have extra power. Sometimes we have to pay people to take the power, right? So now, if you're interested, wait until July. Go to the Midwest system operator website. At night, you'll see negative prices popping up as people are being paid to take power. So extra power is also not that good. Right? Not enough power is not good. Extra power is also not that good.
Interesting. Thank you.
Right? So yeah, so power imbalance is bad. Right? If you have extra power, things blow up. If you don't have enough power, you have blackouts. Right? So neither is good. That's why we have a lot of hope for storage and something like electric vehicle that may act like storage. So really, if you look at a lot of research in power system nowadays, is how do we make use of storage? Storage still being fairly expensive. How do you make use of storage on electric vehicles? I do some research along these lines. Professor Kirshen does research along these lines. So all this is what we're thinking about. But the high level thing is extra power is still not very good. So when the right amount of power, not too little, not too much. Okay. All right. So next, let's connect back between the turbine and we've been talking about before, right? So before, if you remember, we said the power in wind is half delta A speed cubed. Right? So this is the total amount in the moving mass of air. Of course, we don't get this whole amount, right? So no turbine will capture 100% of the power in the air, right? So this is like a solar cell, you can't capture 100% of this solar energy. So we only capture some of it. And the way we write how much we capture is, so we write the power actually goes into the blade as a coefficient multiplied by the power of wind. So this is called the coefficient of performance, right? So this is a measure of how much power you capture compared to the total available amount of power. So obviously this is a number between 0 and 1, right? So you capture some fraction of the power in this. Okay. Right. So this CP itself, this is not something we can compute easily. So we don't have so we can have a first principle way of doing this. In practice, that'll be way too complicated. So what we do is we want some idea of what CP is without doing a first principle computation. Okay, so we want to relate CP to something we can control on the wind turbine. And the something we can control on the wind turbine turns out a good number to look at is something called the tip speed ratio. Called tip speed ratio. Well, the tip speed ratio says the following: is we can look at this number. That's a division. So this tip speed. So this W is wind speed, right? And the tip speed is basically how fast your blade is moving, the linear speed which that your blade is moving. So this is the speed of the tip of the blade, and we want to look at this ratio. Okay, we want to look at this ratio. The reason we want to look at this ratio is this is actually an easy number for us to measure. Right? What we want to say is, we want to measure this number. This number is easy to measure because it only requires us to measure the wind speed, which is a lot simpler than measuring the wind velocity. Getting the direction of wind much harder than say just measuring the speed. Wind speed is something we can measure. The speed of the tip of the wind blades is also something that's easy to measure and easy to calculate. Okay. So any idea how we calculate this? So remember the feedback algorithms, most of them uses lambda measure. This will give us a relative measure of how fast the blade is turning respect to the wind speed. So how do we calculate the speed of the wind of the tip? Any idea?
An accelerometer in the tip of the blade. I don't know.
Too hard.
Is it
Right,
like
so-
the according to the centripetal force of the thing?
Still too hard.
Yeah. Okay.
So Hollis is correct, right? So that's, you measure the RPM, right? So at the end of the day, what you have to do is just measure how fast it's turning. Because the speed of the tip is the
The distance around it over the
distance
time.
times the frequency, times the radial, right? Times the how fast it's going, times the angular speed. Right? This just times the angular speed, right? So this omega is your angular speed. R is the length of the blade. Right? So angular speed for sure I can measure. Right? I have a rotor on my wind turbine, so I know the angular speed. I know the length of the blade, so this is something very easily I can compute. And this is more often written as 2 pi n times r, where n is RPM. Sorry, not RPM, RPS. So this is the RPS, or this is, you can think of revolution per second. So I can measure the revolution per second. Then if that gives me the angular speed, radian per second. And then I know the length. So I can measure the tip speed. I can measure speed of the tip. And I can measure wind speed, right? So what this gives us, this gives us a way to think about how to extract the right amount of power from wind. How do we extract the right amount of power? So, okay, so this just typed up. If you look at the coefficient of performance, then you think about it. If we measure a very small tip speed ratio, so this is called the tip speed ratio, TSR. So if we measure a very small TSR, do we extract a lot of power? So if my blade is moving very slow relative to the wind speed, what's happening there?
You're not getting most of the power of the wind.
Right, we're not getting a lot of power of the wind because it's turning too slow. Right, so most of the wind is just passing between the blades. Right, I have 3 blades. Most of the power pass, between the blades, so I don't capture, right? So, if it's small, then lots of wind just pass through the blades. Right, most of them are not captured, so we don't have this, right? So then what happens when we have large TSR? So if that TSR is too large, does that mean we capture a lot of power? And so it's going very, very fast compared to the tip speed is much faster than the wind speed. Does that give us a lot of power? Should I just turn the turbine, as fast as I can?
In that case, would it gonna blow up like the video?
So suppose I can dump the power. I said, suppose somehow I can get rid of the power. Should I just make it go faster and faster? Should that be my goal of my controller?
I think you still shouldn't do it that way, right?
Right, so why not? Right, so if this happens, yeah.
At that point, you're using power to make it go faster than the wind is, right?
Not really, not necessarily. So what happens is you have going too fast. As what happens? The next blade arrives too quickly. And what happens here is if it arrives too quickly, this basically what happens to his turbulence. Previous blade. Okay, so if this goes, right, we have 3 blades that's turning. So if you turn very, very fast, what happens as the blade turns through a area in air, part of the air, it creates some turbulence behind the blade. And you don't want the next blade to come in and just hit this turbulence. Right? That doesn't give you much power. You don't want to hit turbulent air. So if you turn very fast, then that's also not good. So what happens is you want the tip speed ratio to be, again, not too large and not too small. So if you look at the amount of power generated as a function of TSR, or the coefficient performance, there sort of is a max coefficient performance you can hit through a TSR. Right? So this is a TSR in the middle that gives you a max performance. So here again, this is P blade over P wind. So you don't want to turn very slowly, letting all the wind escape between the blades. You also don't want to turn very fast, right? And just hit everything. You also don't want to turn very fast and have lots of turbulence. So what you really want to do is you want to track this. Right? So what you want to do is you basically want to keep track of the maximum performance, and you want to change your tip speed ratio. You want to have the correct tip speed ratio. Questions? Okay, so this is right. So there is some maximum you can extract from this. Turns out the maximum is not 100%. Okay, so you cannot extract 100% of power. We're far away 100%. So there is actually a theoretical limit that's quite strong. This is a quite strong limit. So there is a best limit. That's a CP max. The maximum power you can extract from a wind turbine is about less than 59%. So normally, of course, we don't get to 59%, but there is a theoretical limit that tells you that the best you can do is probably 59%. But we won't cover here, but this week there'll be a homework question that walks you through how you derive this limit. This is a very general limit. So again, knowing a limit is useful, right? Because it tells us how well we're doing. So if somebody tries to sell you a wind turbine saying my turbine is 65% efficient, that's not possible. So there's a theoretical limit with this. And you'll see how this limit is derived through the homework. It's actually quite simple. It's a very elegant calculation. It's very elegant calculation to get this limit. And we'll walk through that. You'll walk through that in the homework. So our goal is going to track the maximum coefficient performance, knowing that the maximum we get is less than 59% of this. Okay? So now let's suppose we want to track this, right? So let's say we want to track this. Now, of course, even if you started operating as ideal limit that gives you the maximum power, then because the wind speed changes, you will go away from the ideal operating limit, right? So you have stronger wind, your tip speed ratio, your TSR goes down. You have a weaker wind, your ratio goes up, right? So you want to change now the speed of the blade. You want to change the rotation speed of the blade to keep tracking the maximum performance. Okay? So the way you do it is you want to change this number, the rotation speed, and that happens by basically changing the pitch. Okay? So you want to change CP using the pitch angle. Okay? So if you change your pitch angle, then for different pitch angles, this curve, this lambda with respect to CP curve changes. Right? So if I change the pitch angle, then this whole curve moves around. And this curve moving around gives us a good way to actually track. It gives us a good way to track operation node. It gives us a track. And the reason we can track it is because of following. So let's think of why changing the pitch angle give us a way to track it. So suppose the following, right? Suppose we start with some pitch, right? So suppose we start with some pitch. And this is I'm operating at the TSR point A. And now let's say wind decreases. So what happens when wind decreases? Where do you go in your operating point? Do you go left or right? So let's say your blade is spinning at the constant speed, but then the wind speed decreases. So does your TSR increase or decrease?
Decrease.
It increases, right? It's a tip speed ratio divided by the wind speed. So you become higher, but then suddenly this is not the maximum power point anymore, right? We don't track the maximum anymore. Okay, so now we're operating at this red point, which is not as good as before, right? We're losing power. So what do you do, right? So before, I said this curve is beta 1. So now what you do is you change your pitch angle. So now by changing your pitch angle, let's say your curve is now beta 2. Okay? I've changed your pitch angle beta 2. But then you're still operating at this point at the different pitch angle. So your actual point of operation here is at this blue point. And by changing the pitch angle, you're still tracking the maximum power. So the pitch angle changes, the curve, the CP respect to lambda curve shifts. So your new tip speed ratio, your new lambda value, you can center that. You can sort of still make that the lambda where you extract maximum power. Okay, so this is the idea of the feedback control we have in the wind turbine.
But wouldn't the point still be at the red dot though? It's not gonna go up to the blue, right?
No, see, the red dot is respect to the old pitch angle, right? So if I change my pitch angle, the black curve no longer exists, and I'm looking at the blue curve.
Oh, okay. That's really cool.
Right, so I'm now looking at my blue curve. Because I changed my blue curve, right? Because now I'm operating that blue curve, this TSRB is a good operating point. Right? It's a good operating point.
So you basically make the pitch angle adjusting back and forth depending on the wind, the speed of the wind.
Yes.
That's really nice.
Yeah. So you have the speed of the wind, you change the pitch angle, you can track different power points. But so this is a good where the feedback control comes in. Yeah,
but that's gonna involve a lot of micro technology that's automatically sensing the wind speed, right?
Oh yeah, we have these. Yeah, sensing wind speed is not hard. We have all the sensors where the electronics is not hard. So it's pretty cheap to build this kind of sensors now. The question is, of course, can you build reliable sensors? And two is where I'm drawing here is a sort of vastly simplified picture, right? In practice, we don't have one turbine, we have one farm. So you changing your pitch may cause, a turbine that's, let's say 100 meters away, suddenly experience some different wind. So they may change their pitch. And you have one farm. So what we care about is maximize the power coming out of this farm. And so that can be a complicated nonlinear problem. So the algorithm is not easy. But the sensors, the mechanical, controllers, all that is pretty easy. It's sort of not very expensive. This is more on does your algorithm make sense now? Not that can you build a sensor? Yeah, so this gets really complicated. You have one farm, and then what each turbine does influence every other turbine. And that becomes a lot more complicated than what we can cover in undergrad class, basically. But this is the basic idea of wind turbine control. Okay, so now it's a good point to take our break. So let's take a break to 3:32, and then we'll continue with wind turbine after this. Yeah, there will be a homework released tomorrow. So we didn't have a homework due this week, but we'll have a homework due next week. Right, so all right, okay, so let's keep going with this. Right, so here, as you see, we can change the pitch angle to change the power we generate. So for most systems, what we have is we want to generate generate power proportional to the wind power up to a limit. Then we stay at some rated output power. Okay, so the way the power generation curve works is if the wind speed is not large enough, then you ramp up. After that, you operate at some constant output power. Then if the wind really gets too large, you actually have to lock the blade. You have to lock the blade and not turn basically the turbine off. Okay, so most turbines are rated at some output power. You cannot go larger than your rated power. So you have to stay inside your power rating, and if the wind gets too large, there's too much wind for you to operate, so you have to turn it off. So it's, again, not the more wind, the more power you can generate, as you always generate at or less than your rated power for a wind turbine. Right? And so we have this kind of characteristics. We have some speed where the wind turbines start generating power, and after that, the wind power will stay at constant, then we cut it off. Right? So this is here we're trying to hit max CP. Right? We're trying to generate as much power as possible. Then when we hit the rated power, then we want to track the rated power. Then this place where it was called as your lock the turbine, or this is called a feathering, which means you are not trying to generate power anymore. Okay, so depending on where you are, again, the feedback control in your turbine is trying to, either track the maximum power or, be at the correct, or either generate the maximum power or track the rated power of the turbine. Okay, so it depends on where you are, depends on the wind speed, and you operate different ways. Okay, so this is a more detailed description of that. And if you look at the wind turbines, so if you go out and buy a turbine, or you'll get this kind of data sheet that will tell you, given different speed, given the turbine type, this is a curve that you have to follow. Right? Follow this curve. Okay? So anything lower than this curve, this is possible. This area is possible. You can generate at any power lower than the curve. Anything higher than the curve, you cannot do. Okay? You cannot operate at the point that's above the curve, although you can operate at a point below the curve. So this is turbine generation. So wind turbine, is not entirely uncertain, although it is sort of, you have some ramping capabilities, but your ramping capability is limited by the wind speed you're experiencing. So based on your wind speed, you can ramp somewhat, but not arbitrarily, and this depends on the external speed you have from wind. Okay. Any questions about this operating characteristics? Okay, so this is our operating characteristics. Then if you look at the conversion to electric power, right? So basically we have some CP, right? So going from wind power to the blade powering the blades. Now, of course, we have to go through many convergence stages to get electric power, right? So the blade has to go to the gearbox. That's the mechanical power, has to turn the generator. Then we eventually get the electric power output, right? So there's some loss in each of these stages. So in this class, we don't have enough to compute these losses. But again, if you take class like 451, there will compute how much each of these losses are. I'll put some numbers to this loss. For this class, it's enough to know where you're losing power. Right? So in each of these convergence stages, you basically lose some power. So your CP, let's say you have a 40% CP, you turn 40% of the wind power into power into the blades. Then as you may lose, at the end of the day, when you look at electric power, that may only be 35% of the wind power coming in. Right? So you always lose some efficiency here. And then if you look at power, right? So if you look at designing a turbine, then fundamentally you're limited, one by the coefficient of performance, the other is just by how much wind power is in the wind itself. So it depends on the speed of the cube of the wind speed, right? Depend on the cube of wind speed, also depend on the area, right? So the larger the wind turbine I can build, the more power I can potentially capture. Okay, so if you look at the trend today, we're building larger and larger wind turbines. Right? We're building things increasingly in size. Let's increase this A. Okay, to increase this A. Okay, so you look at the table. Now we started at relatively small blades, 27 meters. Nowadays, it's not uncommon to see lengths as close to 100 meters. We're building. And so we went from something like 200 kilowatts to more than 2 megawatts in the rated power. So again, the larger you can build it, the more power you can extract. Right? And they scale like this. So you build bigger turbines. You can build a 10 megawatt turbine if you want. And to give you guys a sense of scale of how large this really is, okay, to give you this sense, this is a picture of a real turbine. So the thing to look at, this is where people are, okay? So we are here, right? So this is a minivan, we are there. And then this is the size of a minivan versus the turbine. This is a tower and the blade size, okay? And this is not a large turbine. This is only a 1.5 megawatt turbine. Right? So if you look at it, this turbine is somewhere here. Right? So imagine how large a 10 megawatt turbine looks to us. Right? So wind turbines are really, really large machines. Okay? And because they're so large, there's a lot of interesting engineering problems that comes out of this turbine. Right? Okay, so these are really, really large. It's because they're so large, and so another way to look at how large this is basically you can put a Boeing 747 inside the blades. Right? So they're larger than the length of the Boeing 747. They're really heavy. They're really large. They sweep out a really large area.
You can fit a 747 in there. Wow.
Yeah, you can fit 747. You can this is a real picture of it, right? So this is a real picture, and I traced out a 747-400. Okay. So these blades are actually longer than 747. So this is a GE blade, and this is again really large, right? To get a sense, look at this is where people are. Okay? People are here. This is how large the tower is. And so these are not small machines, right? They're super large. So what is the limit? right? So can we just build them larger and larger? Right, so what is really limiting you from building larger ones? Right? So let's say you find a really, right? So in the US, right, getting land to build wind turbines is a challenge. So let's say you find a piece of land. Then you basically want to build the largest possible turbine, right? You want to build the longest blades possible to take advantage of, say, the fact you have some land and maybe you have a high wind speed. So what's limiting us from just building, really, really big turbines? Any ideas? Right? What's the number one limitation? Let's say I go and say I want to build a turbine with blade that's 200 meters long.
I think the space. Yeah, you need like a really clear space.
No, I can get space. I can get space. So let's suppose I got some space. I say, you got some land. You want to build a turbine. It's not the fact that we cannot construct towers, right? We can construct, buildings definitely taller than 200 meters. So we can make it. But so I say if I go outside and say, I got the land, right? I want to build 200-meter blade turbines. What's stopping me? Why is that not possible? I guess there are questions for him. Maintenance is what, right? It's hard to maintain. The larger you build it, the harder it is to maintain. Although that's more of a cost problem, so it's not a hard constraint. So it's really not, the reason is a lot more mundane than what you may think. It's really a logistic reason. The reason is really you can't transport turbines that big. You can't translate blades that big. So what you have is really a transportation constraint. I can't get a 200-meter blade somewhere. Right, so our highways are not that large. We can't build that large. Then, construction is difficult. Although sometimes doable, but really what's limiting you is eventually you get into a size where you run out of a truck that can carry your blade. Right, so you're limited by probably the largest blade we can transport on US highways is about 100-meter long. It's about 100-meter long. Longer than that, you're really hard to find a truck that will do it. It's really, really hard to find. Really hard to do that, right? So imagine, right? So if you go to Boeing, you see when they assemble airplanes, how big that hangar is. For a blade that's longer than an airplane, think about transporting that thing. Right? Just not easy to transport it. So on land, we're limited by logistics. Right? I can get a blade, maybe that's 80, 85 meters long to some location, but larger than that, we can't. It's just very hard to do. And then of course you have to install this blade, right? This is another real picture. You have to get this blades up to the tower. Right? So that's like building a skyscraper. You need a crane that can take this thing and install it. So all this is challenging. So this thing on land, we're limited just by the size of the system we can build. Now, of course, if you're limited on land by the size of the system, what you want to do is you want to look at offshore. You want to say, over water, or I can really build larger things because it's easier to transport large blades using a ship than using a truck. Right? So I can build really, really large turbines. Right? So if you look at some of the turbines, that's 20 megawatt or even 10 megawatt, a lot of it's just offshore wind systems. You want to build offshore, logistics is much easier. Also, if you look at where wind is, right? So for wind power, the best wind is along here. That's not necessarily where most people live in the US. But then if you look at offshore, right? So this is onshore. This is onshore. So onshore, most of the wind is along this corridor. then requires a lot of transmission infrastructure to get this wind somewhere in the US. And also what's bad is the US grid essentially splits down the middle along this part. So this is actually, somewhat a no man's land in terms of what the grid is. It's not really connected to anything. Right? So it's hard, we can build turbines here, but it's also hard to get the power out. Where if you look at offshore, you have pretty good wind for most offshore locations. Most offshore locations give you good wind, and actually it's much closer to where people live. Okay? So maybe easier to build a transmission infrastructure offshore than onshore. Okay. So if you look at offshore wind, so you construct a turbine. Offshore, you have to build a cable that connects back onshore. So a lot of challenge is you can build large turbines, but you have to be careful how you do the cable. So how you, you have to construct a power line basically that connects back to some onshore transformer and onshore transmission network. So that may be challenging in itself. Right. So, but again, the offshores are coming, right? All of these turbines are pretty large. We're having more and more projects offshore for offshore wind. So we anticipate seeing more offshore wind farms in the near future. And again, the advantage of offshore wind is basically you have high wind, right? So most places offshore has high wind. You have good match between demand generation. You're fairly close to demand, very close to demand. And transportation is easier. It's easier to get large blades to an offshore location rather than onshore location. So can you think of some of the disadvantages then? Right, there are some good reasons to build offshore wind farms, but what are some disadvantages from building offshore wind farms? What are some of the challenges? Environmental impact, not so much, right? Because the blades are above water, so really not too much environmental impact there. Yeah, so one of the significant drawbacks, I have to build power lines when I build a wind farm, right? So I have a very high investment cost. And I need to build not just the tower and the blade, right? Not just the turbine. I had to build, power lines, I had to build a platform, I had to build everything there. So that's hard to do. And really, another thing is high maintenance cost. It's really hard to maintain, a wind turbine that's doing this, right? Like how do I, how do you fix this, right? If something breaks, how do you go about fixing this? Okay? So maintenance is really hard to do, really challenging to do. And so that leads to a lot of reliability problems. Okay, so I can build it, but again, these machines are very, very large, require a lot of maintenance, right? They tend to break from time to time. But then going to offshore and maintaining these things are non-trivial, right? Very, very non-trivial. So how do you make more reliable turbines for offshore is a question. Right? So how do you make things more reliable? How do you use or engineer better components? How do you use better control algorithms to reduce the wear and tear on these turbines? How do you detect faults maybe before they happen? All these are important questions that we're thinking about. Right? So offshore is good. I think there's a technology that's being more and more popular, although there's still a lot of engineering questions we need to address here. Right, so and again, if you look at the onshore, so all these skip this. If you look at the onshore wind farms in Washington State is pretty good for wind, right? We may not be all that good for solar. For wind, we're pretty good. And we're starting to see a lot of development for wind power. Wind power. But then again, you always have pushback when you talk about this wind power development, right? There are always some concerns. And so as to finish wind power, let's think about what are the possible environmental concerns. So if you build wind power, if you build a wind turbine, what do people complain most about? Birds, they complain, but if you look at the statistic of the number of birds that hits a turbine, it's actually quite low. So it kills,
the noise of it.
Noise, right? Noise is number one. It's very, very loud. It's like a jet engine. And so if you ever get a chance to go to a place where you have large wind turbines like rotating at fairly high speed, that's really loud. It's like a jet engine. You can hear it from far away, right? So you really don't want to build it too close to people, right, where they can hear this. So that's a lot of noise. A lot of people don't like the visual look of it, right? So visually, they're not very appealing. Yeah, go ahead.
I just want to say I used to live next to the airport. Yeah. The noise is really loud, really. The flying is every day.
Yeah, so the similar thing, right? If you build wind turbine too close to a town, then you hear there's no end to the complaints you hear. They're just so loud. Right? So also some people don't like to look at them, right? So that's a real concern. People don't want to see them. Bird is minor. It doesn't really, we don't have that many bird collisions for wind turbine. It's sort of a minor deal. But another thing that may be an issue, also for Washington, but more so for Midwest, is ice accumulation. And what happens if you have a lot of ice and this thing started rotating? What happens is you have missiles, basically. Right? So this sort of launches the ice that's formed on the blades everywhere. So you really have to, heat the blades. You have to be careful you're heating the blades to do de-icing, and don't let us accumulate, don't launch missiles to people, things like this. Right? So there are, some concerns with building wind turbines. Right? So, but still, wind turbine looks to be a fairly promising technology. We'll probably see a lot more growth in the next 10 years or so, right? Both onshore and offshore. Right? So again, the hope is we can eventually have field trips. Before, we used to go and take a field trip to a wind farm and get engineers there to explain things to us. So hopefully that will happen, not this quarter, but maybe in the fall quarter. We'll organize a field trip to either go to a hydro power station or a wind station to have a look at these things. Right, so any question about wind power generation?
Do you know how fast the tip speeds get for like those 10 megawatt turbines? Is it like crazy fast?
No, those are not crazy fast, right? You don't want to spin those things that fast. So those where you can have, it's about 650 RPM or so for the very large one. I think 50, 60 RPM, their rotation speed. So it's not that fast. Yes, it's not crazy fast.
It shouldn't be that fast. It makes sense though, because if it would be fast, imagine if like flying downward, like when it's broken. That's just scary.
Yeah, so so it's not that fast, right? So you don't, things are not that fast. You have fairly slow speed for the turbines are not that fast, especially the large ones. The large ones use synchronous generators, and their rotation speed is in the tenths per minute, right? The RPM is tenths per minute. It's not that fast. So later in this course, we will see, right? So if you think of the grid is 60 hertz, right? So it's 3,600 RPM if you look at the grid frequency. And for the large turbines, you are nowhere close to 3,600 RPM, right? You're very far away from 3,600, right? So you may be at 60 RPM. So how do you, link something that's going at 60 RPM to a grid that goes at 3,600 RPM as also part of the engineering questions, how you engineer this generator. And we'll get to this when we talk about synchronous generators. We'll talk about how do you have a relatively slow mechanical rotation speed connect to a grid that's pretty fast. So when we have small turbines, they go pretty fast. Small turbine can go at maybe 900 RPM or so. Large turbines are slower. Any other questions? Okay, all right, good. So let's end the class here today then. So next class we'll start with hydropower. Right, so we'll keep looking at different kind of generation technologies. So next class we'll look at hydropower. After that, we'll look at more conventional generators. And after that, we're going to transformers. Right, so it will be a homework this week, fairly short homework posted tomorrow. And then I'll see you next Monday.
Thank you.
All right, thanks guys.
Thank you.